Now let's look at some exercises, not problems, to subsets. Let n be the set of natural numbers, z be the set of integer numbers, q be the set of rational numbers, and r be the set of real numbers. Please pause the video and think about why this particular subset criteria works. The set of natural numbers is a subset of the set of integers, which in turn is a subset of the set of rational numbers, which in turn is a subset of a set of real numbers. Let's revisit the definition of what a subset is. A subset is if A and B, for every x that belongs to A, it also belongs to B. For every element that A has, that particular element also belongs to B. Then we say A is a subset of B. So coming back to this particular scenario, the set of natural numbers 1 to n is a subset of integers which runs from minus infinity minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. Over here you have your natural numbers. So every element of set n natural number is also an element of the set integers. Hence, n is subset of z. Let's look at the second criterion over here. Z is a subset of the set of all rational numbers. Rational numbers are of the form p by q, where q is not equals to 0. Now we can rewrite every integer as p by 1, right? And thus, every element of set z is a subset of set q, which is the rational number. Now we come to the last criteria. The real number consists of everything from natural to non-recurring, recurring numbers, including decimal points, fraction, everything. So every element of q is a subset of the real numbers. Hence, we combine all these three together to get the above criteria. Obviously, the definition of a subset, we discussed this in our second lecture, obviously, but still I'm going to repeat it once again. Given the definition of a subset, obviously the set itself is its own subset. If you take a look at the definition, for every element of a set A, it's also an element of set B, then A is a subset of B. We can essentially just replace B with A and this statement will still be true. Hence, for any set, A is a subset of A. Think about this very carefully. The empty set is also a subset of itself. These 2 points bring us to a very significant fact that let A be any set, then the empty set is a subset of A. To verify if this statement is true or false, let's once again rewrite the definition for the subset. You have 2 sets, A and B, and for all x, which is an element of A, that x is also an element of B, we say that A is a subset of B. Please, I have used a very shorthand notation over here. This means for all. Now, if this is the definition of a subset, and this, by writing this notation, you mean that A is a subset of B, what do you mean when you write this exactly? A is not a subset of B, which means there exists an element x which belongs to A, but that element does not belongs to B. This symbol stands for there exists. This particular symbol means, if I have to spell it out in words, then it means at least one element of A that is not an element of B. Now we get back to the problem. If let A be any set, then the empty set is a subset of A. Let's try to prove this by a very well-known technique of proving, like proof by contradiction. Let's refute this statement. The empty set is not a subset of A. That means there exists at least one element of the empty set which is not an element of the set A. And here is the contradiction. By definition, the cardinality of phi is 0, which means phi contains no elements. Hence, we have arrived at a statement which is false. Hence, our initial assumption is false. Hence, we can say the empty set is a subset of A. This technique is known as proof by contradiction. We will be looking at in this types of techniques of proving a mathematical statement and further details, but that's for another day. Let's focus specifically on subsets. Because why am I focusing too much on subsets? Because sets form the building blocks of advanced math. Anything that you would like to do in higher math, it requires you to deal with sets and be very, very fluent in the concepts. Let's try a visual exercise where we will try to visualize the subsets of a particular set. Let's take that set as A, B, C. So S is a set. It has a cardinality of 3. It has 3 elements A, B, and C. We start off with an empty set. We have already established the fact that this is subset of S. So we will start from this very particular premise, and we can always say the empty set as just curly braces. So let's start with a curly brace. Let's ask at every step if we can insert an element into this set. Obviously, we have two choices at every step. Either we can have that element in that set, or we do not pick that element in the set. So let's say, ask the question, pick A. If the answer is no, then we do not. If the answer is yes, then we have an A over here. Similarly, here we ask the question, pick B. If the answer is no, it remains an empty set. If the answer is yes, we have B over here. Once again, we ask, pick C. If the answer is no, it remains an empty set. If the answer is yes, we have C as a subset. Now, in this particular branch, if we ask the question, pick C, if the answer is no, it remains as B. If the answer is yes, then we have B and C. Now we get back to this lower branch where we started off by picking A. Once again, pick B, no. We remain with A. Pick B, yes. We have A and B now. Similarly over here, pick C, no. We remain with A. Pick C, yes. We end up with A and C. Similarly, once again, we ask ourselves the question, can we pick C? We end up with A and B. And if our answer is yes, then we end up with A, B, C. The results that you get at the end of this entire expanded tree is the subsets. So if you count them out, you have in total 8 subsets of a set with 3 elements. So we have a set S, 3 elements, and the number of subsets is 8. I would like you to pause the video, take a little bit of time and think about if S had 4 elements. Try to draw this tree out and check how many subsets do you end up with. Similarly, if S had 5, please check how many elements you end up with. Please explore this way of visualizing the tree and try to come up with the number of subsets. Do you see a pattern? I'm sure at the end of expanding the entire tree for 4 elements, you would have ended up with 16 subsets. Similarly, for 5 elements, you are ending up with 32 subsets. See a pattern over here? For 3, you have 8. For 4, you have 16. For 5, you have 32. If you go on increasing the number of elements, you would quickly see for 6, you will have 64, for 7, 128, and so on and so forth. Can we claim the number of subsets of a set with n elements is 2 to the power n? Let's try to prove or disprove this claim. Thank you so much for tuning in, folks. If you enjoyed today's video, make sure you hit the like button. It really helps the channel out. Don't forget to subscribe and ring that notification bell so you never miss out on our upcoming content. Have a question or want to discuss further? Drop a comment below. I'm always eager to delve into these problems with you. As always, thank you for your support, and we will catch you in the next video. Stay awesome.